Okay, we're going to start with the bipolar junction transistors today. The first section that we're going to discuss is the BJT structure and the basic BJT operation. If you refer to your textbooks, as I will show here on the board just now, you can underline, as I've shown here, the introductory paragraph. The introductory paragraph says the basic structure of the bipolar junction transistor, BJT, determines its operation characteristics. In this section, you will see how semiconductor materials are used to form a BJT, and you will learn the standard BJT symbol. So that's what we're going to cover in this section, a part of it. Okay, if we go back to the first figure in this chapter, there's the basic BJT construction. Referring back to the textbook again, I tell you just above this figure that I'm showing, the BJT, which stands for bipolar junction transistor, is constructed with 3 doped semiconductor regions separated by 2 p-n regions as shown in the epitaxial planar structure in figure 4.1a. The 3 regions are called the emitter, base, and collector. Alright, so there we can see it. First one is NPN, 2 pieces of N material, much larger than the P-type material, which forms the base, which separates the 2. And the 3 materials have got the terminals connected to them, and then they are called collector. You can see there's the collector and the base and the emitter. Alright, this is for the NPN. 2 N-type materials separated by a P-type material. For the PNP, I can see there's 2 P-type materials separated by N-type material, but the terminals are called the same: collector, base, and emitter. Alright, below this figure, this is for interest's sake, you don't have to be able to draw that figure. So that's why I'm just crossing it out. It's not that you shouldn't look at it, it's just that I won't expect you, or you won't be expected to be able to draw that figure. Anyway, if we refer back to the textbook, you can see just below that figure, the PN junction joining the base region and the emitter region is called the base emitter junction. And the PN junction joining the base region and the collector region is called the base collector junction. A wire lead connects to each of the 3 regions as shown. These leads are labeled E, B, and C for emitter, base, and collector, as we've seen in that figure. The base region, this is very important, please underline this. The base region is lightly doped and very thin compared to the heavily doped emitter and moderately doped collector regions. Right, we will discuss the reason for that just now. Okay, so keep that in mind, that is very important. Alright, what we've seen here is there's the base collector junction between the base and the collector. Here's the base emitter junction between the base and the emitter. But please keep in mind, this is very important, that this base material, the P-type material for the NPN transistor, and the N-type material for the PNP transistor is very thin in comparison with the collector and emitter material, and also lightly doped. The emitter is very heavily doped and the collector is moderately doped. So just keep that in mind. We will discuss in a few moments why that is so. Alright, then of course this is important. You have to know the standard BJT symbols. Here we can see is the symbol for the NPN, collector, base, and emitter. You can see that the arrow is pointing outwards for the NPN at the emitter, and here's the PNP's symbol, collector, base, emitter, but I can see that the arrow is pointing inwards towards the base in the case of the PNP. Alright, remember how to use this book. Each section that we do, you have to read through and do the checkup questions at the end of each section, just to test yourself. All right? All right, let's carry on with the next section. It's the basic BJT operation. Let's refer back to the textbook there again, the introductory paragraph. Introductory paragraph for this section, basic BJT operation. In order for the BJT to operate properly as an amplifier, the two PN junctions must be correctly biased with external DC voltages. Very important. In this section, we mainly use the NPN transistor for illustration. The operation of the PNP is the same as for the NPN, except that the roles of the electrons and holes, the bias voltage polarities, and the current directions are reversed. Alright, which I forgot to mention in the previous section, of course, bipolar refers to the fact that both holes and electrons are used in the current flow. Just keep that in mind. Okay, so if we refer to figure 4.3, remember what we've read there in the introductory paragraph. In order for the BJT to operate properly as an amplifier, we use a transistor as an amplifier, and mostly as an amplifier and as a switch, okay, which we will discuss in full detail. But for it to operate properly as an amplifier, I need to bias the transistor first. I need to switch it on. And we will discuss that in full detail as well, why it has to be so. Alright, so I can see I'm using two separate DC supplies in this case. It's not always like this. Actually, it will be different. I can see here at the base, remember this terminal is called the base. I've got a supply, and I also have another supply that is connected to the collector. Remember, we've seen that the base emitter junction should be forward biased and the base collector junction should be reverse biased. Now, look at the polarities. You've learned about the voltage sources. So I can see that I have a negative, positive, so the current will flow in this direction. And remember, these are all connected to earth, so actually all these are connected. So I can see that the current will flow in that direction. I basically have, remember, I've got two PN junctions, three materials, NPN. I'm looking at the NPN firstly. So what do I have here? It's N, P, N, so it's P and N. And you've learned to forward bias a diode, I apply a positive voltage to the P-type material. So the PN junction in this case is forward biased. And as you have learned, I should have approximately 0.7 volt drop over that forward biased PN junction. Right, another thing that I've seen is I have another supply here. So I'm looking at a series circuit on the collector side with the current flowing in that direction, which is supposed to give me the base collector reversed biased situation. But what is bothering me at this stage is I have a supply here, current flowing in that direction, and I have a supply here with a current flowing in that direction. How is it possible that I'm going to get a reverse bias situation in this case? Also, something that you've learned in earlier chapters, or even in electrical engineering 1, when I have two opposing voltages, what happens? I subtract the smallest one from the largest one, and the current will flow in the direction of the largest one. So remember, this supply at the base, which is called VBB normally, will be smaller than the voltage that is applied at the collector, which is called VCC. So if I have a larger voltage flowing in this direction, then I will have a positive on the collector and a negative on the base. So then I have my base collector reverse biased situation. Okay, I can see here in the case of the NPN is exactly the same. All that I have to keep in mind now is that the current is now flowing in opposite directions. But we will have a look at that as well when we discuss the formulas that we work with. You can see now that the terminals or the terminals of the batteries are turned around. So actually the current is now flowing in that direction and in that direction, and I get the same situation. Here I can see that my base emitter junction is forward biased. Of course, when I go and measure with a digital voltmeter, remember I'm always measuring with reference to ground. So I will measure from base to ground, then I will measure minus 0.7 volt, for instance. And also because the current is flowing in that direction, I have my base collector reverse biased with the polarities as indicated. So don't get totally confused between the NPN and PNP materials. You will see later on that all the formulas and equations that we're going to use are exactly the same. You just have to keep in mind the polarities are now going to be different to do all your calculations. Alright, so if we can refer back to the textbook, I've marked some things here. There's the figure 4.3 that we've just discussed. I've marked that first paragraph. It shows the bias arrangement for both NPN and PNP BJTs for operation as an amplifier. Don't forget the keyword there, it's an amplifier. Notice that in both cases the base emitter junction is forward biased and the base collector junction is reverse biased. You can underline this. This condition is called forward reverse bias. Alright, you can read through the section below that. It's basically what I've explained to you what happens. Alright, if we turn the page, remember we've mentioned earlier we've mentioned earlier that the base material is very thin and lightly doped in comparison with the emitter material, which is highly doped, and the collector material that is moderately doped. Now if we look at this figure on page 166, figure 4.4, let me just try to zoom it in. That's it, that looks better. Alright, let's have a look at this figure. What happens there? Or let me show it on here, then it will be easier for me to make some notes. Alright, we're looking at the NPN again. Remember, for the PNP, the current just flows in the opposite direction. And remember, you have to keep in mind, electron current flow is the opposite of conventional current flow. Now, electron current flow is the way that the actual electrons actually flow, but when we talk about conventional current flow, it's from positive to negative. It's in the opposite direction. Alright, so what we will see here, of course, is the electron current flow. We're looking at how the electrons are flowing. Alright, here we can see again the figure that we've previously discussed. There's my transistor with my VBB supply that I've got on the base, which will forward bias, if I'm looking at the conventional current flow, forward bias my base emitter junction, and this supply will reverse bias my base collector junction. Alright, but remember here, you can see on this picture, actually the actual electrons are shown. So if the base emitter junction is forward biased, the emitter material is highly doped. I can see there's a lot of electrons in this area. And I've also seen that my base material is very thin and very lightly doped. So if I forward bias this junction, what's going to happen? The electrons are going to flow over, want to recombine with the holes in the base material, but because it is so thin and lightly doped, there will only be a few electrons that recombine and causes the current IB. Alright? So what is going to happen to all the other electrons? Remember, emitter material highly doped, much bigger than the base material, which is very thin and lightly doped. Not a lot of recombination that can take place. So what's going to happen? Remember now, I've got a positive voltage there on the collector. So all these electrons all dressed up, nowhere to go. What happens? This large positive pulls these electrons through over this junction and causes the electrons to flow in that direction, and I have a much larger current that flows through to the collector. Okay, you can see it also there with the electrons shown. So the reason why is because the emitter is much larger than the base, heavily doped, base material very thin and lightly doped, and the collector material moderately doped, and I have a large current flowing through this device. So this device I can actually see, I'm looking at the current flow, so it is actually a current amplifier. We will see that also a bit later in the course. So it's actually a current amplifier. Now, because of the way that the materials are doped and the size of the materials, this is the characteristic that a transistor has. Okay, but remember, I have to forward bias the base emitter junction and reverse bias the base collector junction, and this is the action that will take place. Alright, if we refer back to the textbook again, you will read all of that there below that figure. If I could just make it a bit smaller again. It starts on the previous page, how to explain this specific figure. So I would suggest that you read through it and make sure that you understand. And then I want to show you the transistor currents. As we can see there at the bottom of page 166, equation 4.1, you can mark that. IE is equal to IC plus IB. So if I go and look at the next figure on the next page, there I can see the two transistors again with their symbols. Of course, remember, what was this terminal called? That was the collector. This terminal was called the base, and this terminal was called the elector. Thus, the current that flows there is the collector current, this is the base current, and this is the emitter current. And I can see the same on the symbols as well. And if I look at the NPN, at the PNP, at the PNP I can see exactly the same for the collector. There's my collector current. For my base, there's my base current, and the emitter, there's my emitter current. But please note, direction of the current flow is now in the opposite direction. But what is important is to see what happens here. Basically, Kirchhoff's current law. I can see here that IC and IB is flowing in this direction, so that one is flowing in there, that one is flowing in there. So what is going to happen? As we've seen in that formula, IE is going to be equal to IC plus IB. And from that, if I have any two currents, then of course I can calculate the value of the other current. Okay, the same applies on the PNP, of course. It's still IE that is equal to IC plus IB. It's just the current flows in the opposite direction. I just have to keep in mind the polarities of the currents. Alright, so important to know the different currents, direction of the current flow for the two devices, and of course I have to know the symbols as well. So again, as I said, read through this section, work through the examples in this section, do the relevant true-false quiz, circuit action quiz, and self-test questions at the end of this chapter. It will be in this whole book, as you've seen previously. All at the end of the chapter, we have all these questions that you can do to test yourselves, and then keep in mind, very importantly, to do the basic problems at the end of the chapter to test yourselves. For the section that we've done, you have to do basic problems 1 to 6. If there's any problem that you can't do, refer back to the section, go and read again, and try to understand before you try the problem again. So that's how the learning process will take place. If you still can't do it, we can discuss it in the class. Maybe there's something that you don't understand, so I can explain it to you again.